Hello, welcome to part 6 of our discussion on steady state error. And the topic that we're at, or where we are with this topic right now, is we're organizing this so that it's easier for us to come back to and actually discover what the steady state error is by using tables to evaluate what we'll see as steady state error. So there's I've already mentioned the fact that, I think it was in the last slide, that the type of the system is applied to the open loop system, not the closed loop system. And it's the number of free integrators in the denominator of the open loop transfer function. So that needs to be remembered. Now the other side of the story has to do with how we calculate the steady state error. And for that, to kind of simplify it for us, we come up with what are called static error constants. And we have 3 of them. There's a P, a V, and an A, and they stand for position, velocity, and acceleration. Now, their connection with position, velocity, and acceleration is not so clear, but this is just what they're known as. That's really all you need to know. There's one problem with the position static error constant. We have a constant called K sub P, which is the proportional gain for a PID controller. And so we've got 2 symbols that are the same for 2 completely different things. So to clarify that, or to prevent confusion, what I like to do is add on the KP anyway dash ESS to show that this is the position static error constant for determining steady state error, and is not the proportional gain of a PID controller. So these are the definitions for the static error constants. Why they're defined this way: if you went back and did the analysis like we did for a step input, a ramp input, and a parabolic input for steady state error, you would find out that you need these very quantities to calculate these static error constants. And they all involve the limit as s goes to 0 of the open loop transfer function, GH. But little variations. So the velocity one has an S. Actually, you can kind of see where the terminology comes from, because remember, multiplication by S in the S domain is the same thing as taking the derivative. So the velocity constant should be the derivative of the position constant, and the acceleration constant should be the derivative of the velocity constant. So here we start off with GH, then we have a S, and then we have an S squared for the acceleration static error constant. Now, with these defined, and with the types of the open loop systems defined, we can put all of this into a table. And here's the table. It's in chapter 6 of my book, table 6.3. And it organizes it by input type, which we've discovered, and then also type of the system, which depends, like I said, on the number of lonely S's, free integrators, in the denominator of the open loop transfer function. So what this shows is, it shows our calculation. Well, it gives the calculation for ESS for each one of these things. And then it shows how to calculate the static error constant, or what the static error constants are for each case. Now, sort of a shorthand way of remembering this also is these inputs over here in this column are increasingly complicated inputs. This is a real simple input. It's just on-off, or off-on. And then this is a gradual increase, and then this is an increase that increases as you go along. So increasing complication of inputs. And then these terms going to the right, this is the number of lonely s's in the denominator of the open loop transfer function. So you could look at these as increasingly sophisticated systems. Increasingly complex inputs, increasingly sophisticated systems. So if you have a complicated input, you need a sophisticated system to be able to handle the error. And if you don't have a sophisticated system, then the steady state error is going to have a worse characteristic. So let's look at that. If I have a type 0 system with a step input, this has no single integrators or free integrators in the open loop transfer function. I will have a constant steady state error. And we saw an example of that before. If I have a step input and I have a type 1 system, this system is more sophisticated, and the static error constant winds up being infinity, but the steady state error is 0. So the more sophisticated system with a simple input, the steady state error goes to 0. For both the type 1 and a type 2, type 3, type 4, whatever you want it to be, you will have a 0 here. I have a constant in this term, I have a 0 here, and I have a 0 here. Now, if we look at this table, back off and look at it a little bit, notice that the diagonal elements are all constants. Okay? But what we have down here in this region is we have a simple system with more complicated inputs. And what that means is that the steady state error is going to be infinite. So the system is not sophisticated enough to handle the complication of the complicated input. And by the same token, over here on the other side, we have complicated systems with simpler inputs. So in the upper right-hand corner, you will have zeros for your steady state error. And in the lower left-hand corner, you'll have infinity for your steady state error. So this is the region of sophisticated inputs, simple systems. This is the region of like complicated inputs with simple systems. This is the region of simpler inputs with more sophisticated systems. Now, there's one other little lurking problem in here, or mistake that you can make in here. Notice that for the expression for steady state error, if you have finite steady state error, which means that you're along the diagonal, is for ramp, it's R0 over KV. For the parabolic input, it's R0 over KA. But it's different for the step input with a type 0 system. So I don't just have R0 over KP, I have this extra 1 right here. That's a common mistake to make. You know, you're used to these expressions for steady state error for these other cases. But with the case of finite steady state error, type 0 system step input, you actually have an extra 1 there. And where that comes from, if you go back and look at the analysis of that case, we did do that. You see that extra 1 right there that kind of screws things up. Anyway, let me go on. I think we're about done. Yes. Last slide. Now, in this example where I did the examples, actually, I did not use MATLAB Simulink for this, or Simulink for this, which I could have, and actually in the book you will see that the examples are done with Simulink. But there are enough applications and companies out in the real world that do not have access to MATLAB Simulink because that program is expensive, especially for a commercial operation. For an academic operation, it's less. It's still substantial, but there's a wonderful open source program that you can use in lieu of Simulink called Modelica. And I've used this program also once I learned about it, and I'm trying to, in these videos, make them more general or useful to people that may be working in industry and don't have access to MATLAB Simulink without spending thousands or tens of thousands of dollars. And you can actually do a lot with Modelica that you can do with Simulink, and in some ways it is more useful because you have complete access to the source code when you're using an open source package. So look here for more examples using MATLAB, or sorry, using Modelica 2. In fact, I'll probably at some point do a series specifically on Modelica and how you use it. Okay, that's my pitch for open source software. We're done here. Keep looking, subscribe to the channel. More and more videos are going up all the time. Thanks a lot for watching.